Internal combustion engines require fuel, spark, and compression to operate. This module will show you how spark is created and controlled in the engine. Producing a spark and having the spark occur at the right time and place is the job of the ignition system. The main components needed to produce a spark include a battery, ignition switch, ignition coil, ignition control module, engine control module, spark plug, and wires to connect them together. A spark occurs when the circuit going through the ignition control module is disconnected from ground. The ignition control module provides this function as shown in the animation. The operation of the ignition control module is directed by the ECM-PCM. The ECM-PCM determines when the spark should occur based on input information from sensors. Basic ignition timing is determined by engine speed and intake manifold pressure. The piston stroke for each cylinder is also needed to know which spark plug to fire. Engine coolant temperature, intake air temperature, and knock sensor input is used to adjust basic timing when needed. This module covers the sensors used to indicate engine speed and fluctuation, piston position in a cylinder, and engine knock to the ECM-PCM. A position sensor can be used to detect position and speed of a crankshaft or a camshaft. Detecting the position of a shaft during its rotation is needed for both ignition and fuel injector timing. Knowing the position of the crankshaft and camshaft allows the ECM-PCM to also know the position of the pistons in their cylinders. Knowing engine speed and fluctuations in engine speed can also be used to determine if a misfire occurs. Examples where a position sensor may be used for the ignition system include the crankshaft, camshaft, and distributor shaft. There are three types of position sensors currently used on Honda and Acura vehicles. They are magneto-inductive, Hall effect, and magnetoresistive. These three sensors all provide the same function, but each does it slightly different. A magneto-inductive sensor operates like this. The magnetic field in the sensor extends through the housing at the tip of the sensor. As the metal tooth of the sprocket, gear, or pulsar moves through the field, a voltage is produced in the sensor. This voltage is an AC voltage. As seen on a line graph of an oscilloscope or scanner, the voltage output would look like this. The shape of this graph is referred to as a sine wave. The faster the speed of the tooth moving past the sensor, the higher the voltage and frequency of the sine wave. A magneto-inductive sensor contains a permanently magnetized iron core with a coil of wire wrapped around it. As each tooth of a sprocket approaches the sensor, the magnetic field moves toward the tooth and a positive voltage is induced into the coil of wire. As the tooth lines up even with the sensor, the magnetic field stops moving and the voltage drops to zero. Then, as the tooth leaves, the magnetic field moves back toward its original position and a negative voltage is induced. This produces the AC sine wave you see on an oscilloscope. The signal is sent through a shielded wire to the ECM-PCM. This type of sensor is most often used for shaft speed since the signal frequency is directly proportional to the speed of the rotating shaft. On some models, it may be used to indicate which cylinder to fire and may be referred to as a cylinder position or top dead center sensor. A Hall effect sensor operates like this. As the tooth of a sprocket or gear lines up with the sensor, the magnetic field movement is detected by the sensor, and an output voltage is seen by the ECM-PCM. As the tooth moves past the sensor, the output voltage drops to zero. This produces a square wave pattern when viewed on an oscilloscope. A Hall sensor consists of a Hall integrated circuit, which is sometimes referred to as a Hall switch. In addition, the sensor contains a magnet, transistor, voltage regulator, and load. The magnetic field movement when the tooth lines up with the sensor produces a voltage, which causes the Hall switch to complete the circuit to the base of the transistor. With the base energized, the transistor completes the circuit, and the ECM-PCM sees the output voltage from the voltage regulator. When the tooth moves away from the sensor, the magnetic field shifts back, and the Hall switch opens the circuit to the base of the transistor, which in turn opens the circuit from the voltage regulator, and the ECM-PCM sees 0 volts. A magnetoresistive sensor operates like this. As the tooth of a sprocket or gear lines up with the sensor, the magnetic field movement is detected by the sensor, and an output voltage is seen by the ECM-PCM. As the tooth moves past the sensor, the output voltage drops to 0. This produces a square wave pattern when viewed on an oscilloscope. A magnetoresistive sensor consists of a resistor bridge and Schmitt trigger. In addition, the sensor contains a magnet, transistor, voltage regulator, and load. The magnetic field movement, when the tooth lines up with the sensor, changes the resistance, which causes the Schmitt trigger to complete the circuit to the base of the transistor. With the base energized, the transistor completes the circuit, and the ECM-PCM sees the output voltage from the voltage regulator. When the tooth moves away from the sensor, the magnetic field shifts back, changing the resistance and opening the circuit to the base of the transistor, which in turn opens the circuit from the voltage regulator, and the ECM-PCM sees 0 volts. Increased power, fuel economy, and reduced emissions can be produced in an engine by advancing ignition timing. However, too much advance causes detonation, which is commonly referred to as engine knock. Mild knock reduces power, wastes fuel, and increases emissions. Harsh knock can destroy engine parts. A knock sensor detects the irregular vibrations caused by detonation and produces a specific voltage signal. When the ECM-PCM receives the electrical signal indicated that detonation is occurring, it retards ignition timing. There are 2 types of knock sensors used: resonant and non-resonant. When detonation occurs, a vibration is transmitted through the engine and into the sensor. The vibration within the sensor produces the voltage that is sent to the ECM-PCM and looks like this when viewed on an oscilloscope. The ignition timing is then retarded to eliminate the knock. The resonant-type knock sensor contains a piezoelectric ceramic. The piezoelectric ceramic is made from lead, zirconium, and titanium. A diaphragm supports the brittle ceramic. When the vibration reaches the ceramic, it causes it to flex. The flexing causes the ceramic to generate a voltage signal. The signal is sent through shielded wires to the ECM-PCM. The non-resonant knock sensor also contains a piezoelectric ceramic made from lead, zirconium, and titanium, but is much thicker. Instead of a diaphragm, it has a weight. A 5-volt reference and return form a parallel circuit through the piezoelectric ceramic, and an approximate steady voltage of 4.7 is seen by the ECM-PCM when knocking is not occurring. When a knock vibration reaches the weight, it exerts a force on the piezoelectric ceramic, causing an AC voltage signal on top of the 4.7 volts. The signal is sent through shielded wires to the ECM-PCM. An ignition coil is a step-up transformer. Displayed are 3 variations of ignition coils used on Honda vehicles. Even though these coils all look different, their function and operation are the same. As a step-up transformer, The coil transforms 12 volts into thousands of volts, capable of jumping across a spark plug gap, creating an arc sufficient to ignite an air-fuel mixture under compression pressure. Although ignition coils may look different, they all provide high voltage to arc across the spark plug. The operation of the coil starts with a 12-volt circuit through the coil, which is used to develop a strong magnetic field around the coil. Cutting off the 12-volt current flow through the coil causes the magnetic field to collapse rapidly. This rapidly collapsing magnetic field induces high voltage in the circuit leading to the spark plug. The high voltage causes an arc to jump the spark plug gap. Ignition coil construction starts with a soft iron core made up of laminated sections used to concentrate magnetism. A coil of thick wire with few turns is wrapped around the core. It is connected to a 12-volt power source and is called the primary winding. Also wrapped around the iron core is another coil made up of a larger number of turns of very fine wire. This is called the secondary winding. When current flows through the primary winding, it creates the strong magnetic field which extends beyond both windings. When current flow is turned off, the magnetic field collapses inward rapidly across the windings of the coils, developing a small amount of voltage in every turn of wire. Because there are so many turns of wire in the secondary winding, the total amount of voltage induced in it becomes very high. As the lines of magnetic force continue to collapse, the voltage developed continues to get higher until it reaches the thousands of volts necessary to jump the spark plug gap. This section deals with the ignition control module, usually called an ICM. ICMs come in a number of different configurations. Externally mounted ICMs, ICMs mounted inside a distributor housing, and ICMs built into the ignition coil. The function of the ICM is to turn the primary current flow on and off to control the magnetic field in the coil, allowing it to produce the high voltage necessary to fire the spark plug. The ECM-PCM determines when the spark plug should fire and operates the ICM. It first signals the ICM to turn the primary current on, creating the magnetic field in the ignition coil. Then, at the exact time the spark should occur, the ECM-PCM signals the ICM to turn the base off, turning off the primary current, causing the magnetic field to collapse and fire the spark plug. The main device inside the ICM that turns the primary current on and off is a transistor. The transistor is operated by an integrated circuit chip, usually called an IC. To build the magnetic field, the IC receives a ground from the ECM-PCM. The IC powers the transistor's base terminal to turn on the current flow from the primary winding to ground. To collapse the magnetic field, the ECM-PCM takes away the ground from the IC. The IC takes away the power from the transistor's base to turn off the primary winding current flow and collapse the magnetic field, which induces the voltage to fire the spark plug. The spark plug provides the spark necessary to properly ignite the air-fuel mixture in the combustion chamber. For this operation to happen, the high voltage coming from the coil travels to the tip of the center electrode in the spark plug. At first, electrical current cannot jump the oxygen gap between the center and ground electrodes because oxygen is not a conductor. However, the high voltage will soon convert the oxygen into ozone, which is a conductor. As the conversion is completed, current arcs across the spark plug gap and ignites the air-fuel mixture. A spark plug consists of a high-voltage terminal, ceramic insulator, steel shell, internal resistor, center, and ground electrodes. Do not assume the spark plugs in a vehicle are correct for that engine application. Spark plugs are specified for a particular engine application due to a number of important characteristics. Use only the spark plug specified for a particular engine. Spark plug reach describes how deep the threads are in the cylinder head. Threads extending past the cylinder head into the combustion chamber may cause serious engine damage, and plugs with not enough reach may cause poor engine performance. Heat range refers to the cooling characteristics, which enable it to operate at the proper temperature. Plugs that get too hot will cause detonation, premature wear, and possible engine damage. Plugs too cold may cause fouling and engine misfire. Spark plugs should operate at a specific temperature. Hot enough to burn off combustion byproducts, but not so hot that it causes pre-ignition. Spark plug electrodes come in a variety of materials. Nickel alloy plugs have larger electrodes and are replaced more frequently than precious metal plugs. Precious metal plugs last longer and include platinum and iridium and have fine wire and ultrafine wire electrodes. The internal resistor is between the high voltage terminal and the center electrode and ensures a target voltage is reached before the spark begins. Improper service procedures may cause many engine performance problems. Follow the service manual for spark plug service procedures such as electrode inspection, gap inspection, thread lubrication, installation torque, and possible indexing. Spark plug indexing refers to the positioning of the electrodes so that they point toward a specified direction in the combustion chamber. There are many variations of ignition systems, but they fall into two general categories. Distributor-type systems use one coil and distribute the high voltage to the individual cylinders. The other system has a coil for each cylinder mounted directly on the spark plug and therefore does not need to distribute the high voltage. It is referred to as a coil-on-plug or COP system. The coil and ICM on distributor-type systems are most often found inside the distributor housing. The high voltage from the coil is routed to the distributor cap and then to the center of the rotor with carbon points and springs. From the center of the rotor, the high voltage is distributed to the individual cylinder terminals inside the cap as the rotor runs. The individual terminals on the distributor cap are connected to their respective spark plugs with a high voltage ignition wire. The spark plug wires on the distributor cap need to be arranged in the same sequence as the engine firing order. For example, on Honda vehicles, 4-cylinder engine firing order is 1342, and the wires are in that sequence on the distributor cap. If the wires are not in the proper order, the spark plugs will not fire on the correct stroke. On some vehicles, the ICM and ignition coil are located outside of the distributor and require an additional wire to deliver the coil output to the rotor, referred to as a coil wire. The high-voltage components of the distributor-type system require greater insulation to prevent the current from escaping its intended path and creating a short circuit. Observing an engine running in a dark setting is a quick way to find ignition wires shorting to ground. Pulsing high voltage can create a frequency that leads to electrical noise, heard as popping, hissing, and whining by the driver. That noise needs to be suppressed so it does not reach other components, such as stereos, and interfere with their operation. Unwanted resistance in the ignition wires, distributor cap, and rotor can lead to ignition misfire. This is easiest to detect when the engine is under a load, since the voltage must be greater to jump the spark plug gap. Refer to the service manual for specific inspection and service procedures. Coil-on-plug systems use a coil for each cylinder. The coil connects directly to the spark plug. On some COP systems, the ICM is a separate component that has individual circuits to control each coil. Other systems have an ICM built into the top of each coil. COP systems are very reliable because the high voltage goes directly to the spark plug from the coil, eliminating the distributor cap, rotor and ignition wires, as well as the mechanical distributor assembly. Some time ago, engines used mechanical systems to advance ignition timing. However, mechanical systems are not able to fully compensate for varying engine speed and manifold airflow rates. Vehicles today use the ECM-PCM to calculate ignition timing advance for varying engine speed and manifold airflow rates. To understand how engine speed affects ignition timing, Let's start by looking at normal combustion taking place in an engine. Notice that there is a period of time between the firing of the plug and the buildup of enough pressure in the combustion chamber to push the piston down during the power stroke. This event is called combustion pressure time, or CPT. For our learning purpose, we will say combustion pressure time is 0.02 of a second. At an idle of 600 RPM, the crankshaft will turn about 6 degrees in 0.02 of a second. If we want the combustion pressure available at the beginning of the power stroke, we need to fire the plug about 6 degrees before top dead center at the end of the compression stroke. If the engine speed is doubled to 1200 RPM, we still need the 0.02 of a second to develop the combustion pressure. Only now, the crankshaft will rotate twice the distance, or 12 degrees, during the 0.02 of a second. So the plug needs to be fired at 12 degrees before top dead center during the compression stroke instead of 6 degrees. It would seem to follow that the ignition timing advance should be doubled every time the engine speed is doubled. This does not happen because combustion pressure time changes with manifold airflow rates. The amount of air moving into the combustion chamber is defined as manifold airflow rate. Since the throttle controls the amount of air going to the combustion chamber, manifold airflow rate is reduced any time the throttle is not wide open. Opening the throttle and letting more air enter the combustion chamber will increase manifold airflow rate. As airflow increases, combustion pressure time decreases. More air means more air-fuel mixture density. The more dense or closer the molecules are, the faster they react to each other. Faster reaction causes less combustion pressure time. So, less advance is needed as manifold airflow rate increases. As you look at this first advance curve, the vehicle is accelerating very slowly with little throttle opening. During this example, the same vehicle is accelerating with the throttle about half open. Ignition advance is less because combustion pressure time is less. On this example, the throttle is wide open and combustion pressure time is even faster, resulting in less ignition advance. The maximum amount of air that can fill a combustion chamber is usually reached between 3,000 to 4,000 RPM. At that time, no further ignition advance is needed, and total advance usually peaks somewhere between 30 and 40 degrees. When the driver opens the throttle, the map sensor reports the increase in manifold pressure, which results from a larger amount of air introduced into the combustion chamber. Ignition timing is calculated by the ECM-PCM using intake manifold pressure from the map sensor and engine speed from the crankshaft sensor. Proper ignition timing advance can produce increased power and fuel economy and reduced emissions. However, too much advance causes detonation, which is commonly referred to as engine knock. Mild knock reduces power, wastes fuel, and increases emissions. Harsh knocking is more serious and will destroy engine parts if not corrected. This is what causes knocking or detonation. Normal combustion takes place when the mixture is ignited by the spark plug and pressure increases evenly and smoothly and is maintained throughout the power stroke. Detonation happens when the pressures and temperature in the combustion chamber exceed the fuel's resistance to self-ignition. During self-ignition, a short-lived pressure spike occurs as the fuel ignites simultaneously. Too much spark advance can cause the rapid buildup in pressure that causes self-ignition and the resulting detonation or knock. When detonation occurs, the ECM-PCM receives a signal from the knock sensor and retards ignition timing. Since maximum efficiency happens when the cylinder pressure is extremely close to detonation, the ECM-PCM retards the ignition timing only enough to prevent detonation. To confirm ignition timing operation, each engine has an inspection procedure. Poor engine performance, gas mileage complaints, and failed exhaust emissions can all be caused by incorrect ignition timing. Inspecting the ignition timing is a test that will aid in the diagnostics of these conditions. For distributor-type systems, the timing light inductive pickup is installed on number 1 spark plug wire, and the light is aimed toward the pointer on the timing belt cover near the crankshaft pulley. The service manual provides specific procedures and specifications for each vehicle. The ignition timing may be adjustable on some vehicles with distributor-type ignition systems. The mounting bolts for the distributor are loosened, and the distributor is rotated to make the adjustment.